Um, Welcome everyone. So today we are going to begin with the idea of kinetic interpretation of temperature. So in the last video we were discussing that what is the pressure of the gas and more specifically speaking, an ideal gas. So in that case, uh, we basically arrived at the idea that the pressure of a gas is uh, proportional to the square of the RMS speed of the gas particles. So, what does that entail? It entails that we can obtain a temperature relationship with the velocity of the gas particles. And how can we do that? We will basically say that the pressure of the gas, that is P, we can use ideal gas equation. So the equation which we had was P by rho is equal to the square of the RMS speed of the gas. So this expression P by rho, we can replace this by RT by the molar mass of the gas. So this becomes 3 times RT by M is equal to RMS speed square of the gas. So from this expression I can say that 3RT by N or 3RT by 2 is equal to half N VRMS square. So this is the kinetic energy of the overall gas for 1 mole. So this is the total kinetic energy of an ideal gas or 1 mole. So this is equal to 3RT by 2. Um, so from this expression we can directly say, or we can directly uh, get a deduction that the kinetic energy of a ideal gas is directly proportional to the temperature of the gas. So this is a monumental statement for a gas. Basically, a way of relating that how fast the particles are moving. They are directly deciding what is the temperature of the gas. So that means that temperature is not some quantity which we have uh, devised out of thin air. It actually is uh, giving us information about the molecular motion of the particles. If the molecular motion of the particles is very vigorous, it is having high speed, the temperature will be high. If the speed of the particles is relatively less, then the temperature would be low. Second point, we'll say that this is independent of the nature of the gas. We'll say we have not used here any kind of information that whether what kind of gas this is, either it is hydrogen, helium, or nitrogen or oxygen. whatever. The total kinetic energy of the ideal gas is going to be this expression, that is 3RT by 2. So one more term is also there, that is the rotational kinetic energy term. But we can say that the kinetic energy is proportional to temperature. Next, we want to obtain what is the average kinetic energy of a single molecule. So we will say kinetic energy of a single molecule of a gas is equal to 3 by 2 kT. So this value K is the universal gas constant R divided by Avogadro's number, Ne. So its value is 1.38 into 10 to the power minus 23 joule per Kelvin. Ne is Avogadro's number, and R is universal gas constant. This value K is called the Boltzmann's constant. So he is the guy with the funny beard. Uh, I can find his photo in NCRT book. So it is named after him because he did all those research and regarding kinetic theory. Next, we want to do one question. So we basically have a particle. That particle is at the surface of Earth, like this, right? Uh, so we are given that temperature of the particle is T. And assume the particle to be a monatomic gas. Uh, Question is, if the particle is to move vertically upwards on Earth, then till what height will this particle rise to? So that means that we need to find the kinetic energy of the gas and what is the kinetic energy of that particle and convert it to the gravitational potential energy. Now, since that particle is going very high above Earth, that means that we cannot use the case of uniform acceleration due to gravity. We'll have to use the case of uh, the general expression of gravitational potential energy. So, what is the kinetic energy of this gas particle? It would be 3 by 2 kT, because we know the temperature of the gas. This will be equal to the kinetic energy of the gas, and this will be equal to whatever potential energy uh, change has happened to this particle. So, uh, we'll say final potential energy of the particle is minus g capital M small m divided by radius of earth, let's say r, and it is going to reach some height h above the surface of earth, right? Minus the initial gravitational potential energy of this particle. So upon solving, we'll find h, height of the particle above earth's surface. So this is the whole basically a starting expression. What is K? K is Boltzmann's constant. What is T? T is temperature. What is capital M? What is capital M? Capital M is mass of Earth. So that is also given in the question. Mass of Earth is given. Radius of Earth is also given. R is the radius of Earth. So there is a small story in this question. Basically, we can evaluate what is the atmosphere of height of the Earth's atmosphere by using this expression. If we know what is the average kinetic energy of the particles on the Earth's surface, then we can get an estimate to what height will this particle go to using this equation. Next uh, is the 3 kT by 2 is equal to G capital M small m upon R plus H into R. So this will be this is plus 1 by R. The plus 1 by R gets multiplied here, so this becomes minus R plus R plus H. Then we'll say this is 3 kT by 2 is equal to G capital M small m upon R plus H into R into small h. So here we can approximate that key this value h is much smaller than the radius of Earth, or we can find that actually where we have got h here, right? So um, let's say this whole value, this will be R plus H into R, right? They will have an H here and one more H would also be there. So from that we'll be able to obtain what will be the value of small h. If we approximate it, what value we'll get? Upon approximation, we'll get this 3 kT by 2 into r square upon g capital L small m is equal to